This is the one loop problem, so we don't have to use node rule. Okay, because the node rule applied to here only means all the currents are the same through every element. But the loop rule can still be applied. Let's say we start from here. Okay, epsilon. Go down here from here to there, so minus IR. And then minus what? From here to there, because this is positive, this is negative. So again, the voltage drops by how much? By VC. Okay, VC, and that equals 0. That is the loop rule. What is VC equal to? VC equals Q over C. Okay, so VC equals Q over C. Q is the charge on the capacitor. And if you plug that in, you find that this is not a completely solvable equation yet, because you got two unknown functions. There is I as a function of time, and there is also Q as a function of time. Okay, so our job next is to express either Q in terms of I or I in terms of Q, so that we get only one unknown function, then we can solve it. How do you wish to do it? Well, this current is the charging current, right? The current allows a certain amount of charge to be deposited onto this plate, and the rate at which charge gets deposited per unit time is I. So therefore, clearly I equals dq over dt. Right? So this is one way to do it. That is, I'm going to get rid of I in favor of q. Okay, in favor of q. So plug this into here. You will no longer have I, you only have q. So you can solve for q. Once you know q, you can solve for VC, because it's just Q over C. You can see whether you get this type of curve or not. Okay, so let's do that. You can also try to retain I and just express q in terms of I as an integral, but we only choose one way to do it. We just get the same result. Okay, plug both of these into here. Epsilon minus, and then I'm going to move both of these terms to the other side. Okay, the first term is IR, which is R dq dt. The next term, VC, that is just Q over C. Okay, now at this point, all we need to do is some mathematics, and that is we solve this equation for Q as a function of time. Be careful about this equation. This is not a usual algebraic equation. In an algebraic equation, our job is to find a number or several numbers which numerically satisfy an algebraic equation. Okay, so the target that you're looking for is a number. Here, we have q as a function of time. Okay, and in this particular term, it is under a differential symbol. So what we have here is it's not an algebraic equation, it's called a differential equation, and our goal is to find an unknown function, not an unknown number. Okay, be careful about that. Now, there are several ways to attack this differential equation. It's a very simple differential equation, so it's rather simple to do. One of the things you can do is you can do what's called separation of variable, and that is there is q, there's t. Okay, q is a function of t, and t can be totally solved. There is only dt here, nothing else anywhere has t in it. So you can just solve dt for dt. dt equals whatever, whatever, whatever. And then you can integrate. The left hand side only has t, the right hand side only has q. You can integrate, you will find the solution. Okay, we can do that. We can do that. And it's not hard to do, but it's kind of boring. Okay, what I want to do here is some sort of alternative method to solve this problem. Okay, and the way to do that is, if we take a good look at this equation, we say, all right, look, the left hand side is epsilon, which is just a constant. It never changes with time. Now the right hand side, on the other hand, has two variable terms. Q is a function of time. dq over dt is also a function of time. And yet somehow, when you add them together, you don't get a variable anymore. You get a constant. Okay? So, however this term changes with time, and however that term changes with time, their time dependency must what? Must cancel each other out. Okay? That means their time dependency must have similar functional dependency, functional form. For example, it is impossible for dq over dt to be a sine function of time, and yet for q over c to be a tangent function of time, because you cannot cancel them out all the time. All right? So what we're looking for is the solution such that Q and dq dt have the same dependency on time. That is the only way to cancel them out when you add them together. Alright? So the question is, what kind of equation is such that, what kind of function is such that, when you take a derivative, it goes back to its same form? Okay? Does sine function behave like that? No, it becomes a cosine. Okay? Does any exponential function goes like that? No. T to the power 3, for example, you differentiate, you get t to the power 2. So what kind of function? What kind of function behaves like that? The power function doesn't do the job. The sine function doesn't do the job. But what about an exponential function, right? An exponential function does that job, doesn't it? Okay, so our best guess is to say, all right, Q probably is an exponential function of time. Something like, a plus b e to the power negative alpha t. Okay, now you say, you ask, why do we get a negative sign here? Well, I don't have to have a negative sign. I can just call it alpha t if I want to, but then eventually it turns out, if you plug that in, you'll find eventually alpha turns out to be a negative number. So why bother? You just put a negative sign here first. Alpha would turn out to be a positive number at the end of the day. Okay, either way it's fine. This is what's called a trial solution. It's an educated guess, because only exponential functions behave in such a way that when you take a derivative, it goes back to itself, so that these two terms can cancel their time dependency, adding to only a constant. Okay, now let us plug this in here. Okay, plug this in. I have epsilon equals what? R dq dt. Look at dq dt here. When you take a derivative, this term is gone. What about that term? Negative alpha b e to the negative alpha t. There we go. Right. The next term is what? A plus b e to the negative alpha t divided by what? By c. Okay, just a matter of plugging things in. Now, let me clean up a little bit on the right hand side. Okay, there are two types of terms. There's this term a over c. It has nothing to do with time. Okay, over c. And there are two more terms, this guy and this guy. They're both proportional to e to the negative alpha t. So I'm going to take that thing out. Okay, e to the negative alpha t. What do you have here left? You have negative alpha b r, negative alpha b r, and the other one plus what? B over c. Okay, right? Okay, take a good look at what we get here. Mathematically, we want this equation to be valid at any moment of time. But this is the only term in this equation that depends on time. Nothing else depends on time. So as time changes, this guy is going to change. Okay? But this is the constant. That is also a constant. Now that is telling us that you cannot possibly make this valid for all time, not just one time, but all time. Because this is a constant, this is a constant, and yet this next term changes over time. Right? That seems to say this equation is impossible. It's just wrong. Except what? Except if this time variable term does not really exist. In other words, this is equal to what? It is equal to 0. Okay? When this guy is equal to 0, I don't care about it, because whatever t to the negative alpha t, however it changes, this whole thing is 0. So you don't have that at all. But if that is 0, that only leaves epsilon equals a over c. Right? So we conclude that the only way to make this valid for all equations, for all values of t, would be to kill this term. In other words, we want negative alpha r b plus b over c to be what? To be 0. And as a result, epsilon must be equal to a over c, because there is no term left. Epsilon equals a over c. Okay, if we cross out b and b here, you get negative alpha r plus 1 over c equals 0. In other words, alpha is now solved as 1 over rc. Perfect. That's exactly what we suspected before. Okay, so the math here agrees with the physics there. Now, this doesn't tell us what b is, because b crosses out. Okay, it does tell us that epsilon must be a over c, Okay, so we only can find alpha from this equation at this point. So we have the general solution. Q is still a plus b e to the negative alpha t. That still looks like it's a general solution. We haven't fixed a and b yet, but not to worry, we'll figure that out. Okay, how do we figure that out? Look at what happens when t equals 0. At t equals 0, what is the value of q? Okay, at t equal to 0, q is equal to a plus b e to the negative 0. That's a plus b. But wait a second, at that point, shouldn't q be 0? Right? Because there is no charge on the capacitor at t equal to 0. That's how the experiment condition was. So that tells you that a equals negative b, or b equal to negative a. And therefore I can write this q as q equals a, then 1 minus e to the negative alpha t. Okay, things are looking hot, looking better now. This is starting to take shape as something that we guessed. This is VC, this is Q, but of course Q and VC only differ by the value of the capacitance. Okay, the only thing I've left to determine is A. How do we determine A? Okay, you cannot determine A just by looking at what happens when Q equal to T. Q at T equal to 0, we already did that, and as T equals to infinity, on the other hand, what about this term? What about this term? It goes to 0. And that at that time, okay, so t approaching infinity, q is now equal to a. But we know at that moment what q should be. It is now fully charged. The capacitor is now fully charged. If the capacitor is fully charged, how much charge do we have? It should be charged such that the potential difference across these two plates is now what? Epsilon, right? But if that's epsilon, then how much charge should be deposited on it? Should be c times epsilon, shouldn't it? So q at that moment, when it's fully charged, it's c times epsilon. That tells you what A is. A is c times epsilon. There we go. So all in all, q equals c epsilon 1 minus e to the negative t over rc. Okay, that is the solution to q, and that gives us VC. VC, which is simply q over c, and that is just epsilon 1 minus e to the negative t over rc. Now compare this with what we got over here. Our guess. Look at how clever we guessed it without any detailed calculation. We guessed VC should be like this, and alpha should go like 1 over RC. That's exactly what we get. And that VC maximum, as we know, should be the fully charged value of the voltage difference across the capacitor, and that should be epsilon. See, epsilon right here. Okay, so our guess gave us the exact right answer. Okay, this is epsilon, which is VC maximum. All right, given VC and given Q, how does one find the current now? Well, isn't it true that the current is dq over dt? Okay, dq over dt. Now that we know the current, and now that we know Q, this is Q right here. Actually, Q is right here. Full expression. I equals what? dq dt. Let's just take a derivative. Okay, let's just take a derivative. The first term is gone. The next term, negative sign cancels. You get c epsilon over rc, right? C epsilon over rc. C is gone. Epsilon over r e to the negative t over rc. Okay, is that right? Well, let's see. Our guess was I equals I naught e to the negative alpha t, and that I naught, as you know, is the initial current, is epsilon over r. See, epsilon over r. And then e to the negative alpha t, alpha is 1 over rc. So you see our guess here is once again correct. You have an exponentially decaying function for I, an exponentially rising function for VC. Our theory, okay, I goes like this, VC goes like this. Our theory, our calculation eventually confirms the educated guess that we put out for both the current and VC. Okay, now, by the way, what about VR? If you want to know VR, how would you do? VR should be proportional to current. Okay, that's the easy part. VR is just I times R. If I goes like this, then VR also goes like this. As a matter of fact, VR and VC should be complementary to each other. VR goes down over time, VC goes up over time, but the sum of VR over VC is what? Is always epsilon. That's a constant. Okay, so that's why, as one of them goes down, that's VR. The other one has to go up to make up for it. So that is the RC circuit in the charging process. And by the way, R times C, this quantity has the unit of time, and we define it as tau, the so-called time constant. Okay, time constant of RC circuit. Of an RC circuit. A large tau means it takes a long time for the capacitor to be fully charged, and a small tau means the charging process is fast. Now, knowing how to describe the charging process, it is quite simple to extend this discussion to the case of discharging. In the case of discharging, we start with a charged capacitor and a resistor. But we don't have any battery to power anything. Rather, we have a switch which is closed at t equal to 0. So at that moment, the circuit becomes one loop, and the current will start to flow. The current, of course, is now powered by the potential difference across the capacitor, no battery involved. So you have a discharging current, okay, flowing like this. And that current must diminish over time because it's powered by the charges on them. Eventually the charge will be gone and there will be no current flowing. So obviously current in this case should flow like this, obviously. Okay, and what is the initial current I naught equal to? It must equal to, okay, at that moment the initial voltage across it, VC naught over that's at t equal to 0, divided by what? Divided by R. Okay, just apply Ohm's law to that particular moment. It should diminish over time like that. So what do you think? How should I go down as a function of time? Well, it should be, as we learned from the previous case, you can imagine it's analogous to the previous case. I must be equal to I naught e to the negative t over RC. At least that's our suspicion, right? Now what about VC and VR? Well, in this case, VC should go down, VR should also go down over time, but that doesn't matter. That doesn't mean you violate the loop rule, because after all, this time, as you go from here to there, you got VC. But as you go from here to there, you have the minus VR, right? Because the current, the voltage drops down, and that is 0. Okay, that is 0. So here is the positive, and here's the negative. It's like that. And in the past, in the charging case, we allowed the current to flow that way. So at that time, that VR was actually from here to there, and here is reversed. So that's why you have a symbolic difference. Okay, so what is VC equal to? What is VR equal to? They have the same magnitude, right? They have the same magnitude. How should I find VC and VR? We already guessed I. We can also guess VC and VR. They have the same magnitude, so we might as well qualitatively guess what VC should be. That's a function of time. It starts from the initial value and it drops to 0, and it should drop to 0 like that. Makes sense. Okay, so it's once again it's something like 1 minus e to the negative alpha t, something like that. Very similar to the case of charging. To make sure these are actually correct, we can apply Kirchhoff's rule again. So from here to there, it's VC, okay, which is Q over C, and from here to there, okay, from here to there, the current flows this way, so the voltage drops by IR, I times R, and that should be 0. Again, we can get rid of I or get rid of Q, either way. In this case, how is I related to Q? I is the current flowing this way. I is what? dq over dt, but with a negative sign. Okay, because if you have current flowing this way, that's going to cause the charge to diminish, not to increase. So it's negative dq dt. So you plug that in, you get q over c plus r dq over dt equals 0, right? And how does one solve this problem? It's very similar to the previous case. the idea how we solved it. You can solve for dt and integrate, or you realize that this is a function of time, that is also a function of time, yet they add up to 0, a constant. That means whatever time dependency here must resemble the time dependency there. So q and dq dt once again have the same functional dependency on time. That only happens when q is a what? Is an exponential function of time. Okay, so q is proportional to vc. So again, we guess that q should be like q naught 1 minus e to the negative alpha t. You plug this in as we did in the previous page. Okay, plug this in. You will find what q naught is. You will find what alpha is, and alpha will be turned out to be the same as before, 1 over rc. Okay, and q naught is just the original charge at t equal to 0 on this capacitor, and everything will be verified. This is in fact the correct expression. Okay, this is also true. Once you get that negative dq dt, you will get that. Okay, so the discharging would satisfy an equation like that with the same alpha as charging. So the faster the charging, the faster the discharging.